In the previous lecture, we looked at a new way of defining a sequence, one where the definition of each term is given in terms of the value of the previous term rather than the value of n, or its position in the sequence. So in this lecture, we're going to look at two well-known examples of this kind of definition to give you a feel for how it works in practice. So I want to start by looking at the factorial function, something you're probably already familiar with. The factorial function, written in factorial, is equal to the product of the first n non-negative integers. Now, the domain here is clearly the non-negative integer, so the factorial function can be thought of as a sequence defined using our earlier method, where each term is defined in terms of n, that is its position in the sequence. And this is using the product notation. Looks like this. Now, if we apply the method we discussed earlier, where we peel off the nth term, right, we can see that the nth term of the sequence is equal to n times the product of the first n minus 1 terms. But this product is just n minus 1 factorial, which is the previous term in the sequence. So if we replace that expression with a sub n minus 1, we get the exact same sequence, except now it's defined recursively. And to complete the recursive definition, we need to also define the initial value, a sub 0, which would be 0 factorial, which is just 1. So there's two key things I want you to pick up on here. First, it's possible to define a given sequence in multiple ways, right? I've got it defined, we would call this the explicit version. And over here we have the exact same sequence defined recursively, right? So that would be the recursive version. Another thing that I want to point out about the definition here is that not only is the nth term defined in terms of the previous term, but it is also defined in terms of the position number as well, right? And that's okay, right? The key factor to a recursive definition is that the definition of the nth term has to include at least one previous term. If it includes other things, that's still okay. In the early 13th century, a mathematician who went by the Latin name Fibonacci was thinking about rabbit populations. He started with a single young rabbit and made a few assumptions. First, it takes one period, if you will, for a rabbit to mature. And second, post-maturity, every rabbit produces one new rabbit per period. Okay, so if we start with a single rabbit, we start with a single one, and we'll call this period 1. In the next period, we'll still have a single rabbit. That's that first requirement there. This is the period that it takes the rabbit to mature. Right now, in the third period, the rabbit will reproduce for the first time. So now we have the original rabbit plus its offspring. All right, so keep this going. In the fourth period, we have these two rabbits, and this rabbit reproduced again. This rabbit didn't, right? Because he needs that one period to mature and start reproducing. All right, so in period 5, let's do this a little more here. In period 5, these three rabbits are still there. These two are now old enough to reproduce. All right, so let's go one more. If we go one more period to 6, we keep the five original ones, and the three who were in the sequence two periods back are also going to reproduce. Okay, now try looking for a pattern. Right? Every period is made up of the rabbits from the previous period plus an additional number equal to the number that were in the period 2 steps back, because those are also now old enough to reproduce. Okay, this gives us the recursive definition of what's commonly called the Fibonacci sequence. A sub n is equal to a sub n minus 1, right? That's the generation back, plus a sub n minus 2. These are the existing rabbits. These are the new rabbits from the now mature members of the population. So this sequence comes up in a surprisingly large number of applications and natural phenomena. So many that we could easily devote an entire chapter just to this sequence alone. But the main feature that I want you to take away for this class is that recursive definitions aren't limited just to expressions based on the previous term in the sequence. It's also possible to base definitions like we have here on multiple previous terms. Now that we've seen a few examples, hopefully you're starting to get a feel for how these recursive definitions work. So in the next lecture, we're going to circle back a little bit and we're going to take a look at the idea of a series. Remember, a series is the sum of the terms of a sequence. We're going to see how we can use this idea of a recursive definition to come up with a more formal definition of what we mean by a series.